Hello everyone, my name is Tomas Fernandez. I'm a technical writer at Semaphore, and this talk is based on a workshop we did on Belgrade about machine learning, DevOps, and MLOps. Since we don't have as much time, I will assume you have the basics of machine learning and cover all the tools and practices you need to take a model from Jupyter notebooks and deploy it in production in a safe and automated way. So why use MLOps? First, because automation means there's less work for us to do. We can do more in less time. The automation means we also can scale our work, take the same workload and use it on bigger machines without additional work. It also provides consistency because we track everything that goes into the model. We can know exactly what data points were used for training, what scripts and parameters were used to train our model. And finally, we have traceability. We know exactly what datasets went into our training and fine-tuning. Let's start with a quick overview of the machine learning model we're going to use. This is on kaggle.com. I will leave a link in the slides so you can check out the code for yourself. We're using ResNet34, a convolutional neural network, and using the Oxford Pets dataset to fine-tune this model to recognize cats and dogs. I don't want to spend a lot of time here explaining the code because you probably know this very well. The main problem I think Jupyter notebooks have is that they work like Excel. They work great in your machine. They're a great way to experiment and to build and discover data. But when you need to deploy the application, the model into the general public, is not feasible to use it with Jupyter notebooks. So we're going to take everything we have here and put it in pure Python and train the model using continuous integration. So this is the project. I will leave a link to the repository in the slides. This project has all the Python code we need to fine-tune the model, test it, and deploy it. The code is the same we found in the Jupyter notebook with some small modifications. The first thing we're going to need is to download the training dataset. I'm doing that here on the terminal, and this is the first problem we're going to encounter when using DevOps practices on machine learning workflows. The data is big, it's about 800 megabytes, and we can't use something like Git to track this. In theory we can, because Git supports like large files, but we're going to easily reach the maximum amount of data very easily, so we need a different alternative. And to manage the data and to later create the machine learning pipelines, we're using a tool called DVC. So DVC is an open source tool. I don't work for DVC. This is not an endorsement. It's just a tool that I find useful, and it's useful because it lets me track the datasets in Git without actually having to upload the files into Git. It uses hashes and special files to track what data goes into the model. DVC comes for all Mac OS, Windows and Linux, so you can install. It's a command line tool. And as you can see, we have here the file. This is a Git repository, so Visual Studio Code is going to mark this file as pending to upload. The problem is, as I said, we don't want to upload this big file into the Git repository. So instead, we're going to run dvc add and the file. We are going to execute this. So this is going to do a number of things. It's going to create a new file which has the extension dvc, and this file contains the hash for the original file, the size and the path to the original file with the data. And it also has updated git ignore and added the file, so it's not longer going to be pushed into a repository. It's going to be ignored. The other thing it does is to create a cache directory into the .dbc folder. This folder is not to be checked into the repository, it's also to be ignored. But what dbc does is to move the original file into this cache directory and then link it back to the original location. It's going to use either ref links, hard links, or symlinks depending on the file system you have on your computer. In case of Mac OS, it's going to use ref links, meaning that both entry files point to the same part of the disk, so the file is not duplicated. And now what we need to do is to check out the git ignore and the dbc file. So once we push this, we track in our repo which data we are using in our training. So let's pause and check how dbc works. It follows the git syntax and workflow. It ties into the git way of working. Each time you run a dbc add, it will hash the file, move it into the cache, and create that .dbc file as a pointer to the original file. And when we do a dbc checkout, dbc will pull that file from the cache and link it into our working directory, so we can have different branches in our git repository, each with different .dbc files pointing to different datasets, and all the datasets will be stored eventually in the cache, and we will pull from the cache using dbc checkout the correct files every time. So another cool feature about dbc are machine learning pipelines. Pipelines are like makefiles for machine learning. They are versioned with Git, so the whole process to build and train model is stored on Git and tracked there. And all the results, all the intermediate files, all the models, all the transform datasets are stored and cached. dbc will keep track of all the changes and will reuse intermediate files as needed. This is the syntax to add stage. We put a name, which is arbitrary, the dependencies, which are the input files. They can be source code files, database data files, and the outputs. We can also store metrics as a separate entity. And finally, we have the command that runs. In this case, is a Python program that cleans up the input data. The stages are stored in a file called dbc.yaml. It can be checked into Git, and it tracks all the stages, the inputs, outputs, and computes the dependency graph. The pipeline is stored in a file called dbc.yaml, which can be tracked with Git, and it tracks the inputs, outputs, and builds the dependency graph automatically. Okay, let's see pipelines in action. Instead of tracking the images storeable, I'm going to track the output of these files. So what I have here is a prepare script, which basically unpacks the tarball into separate images. So I'll start by removing the tarball from the dbc cache. We need to remove the .dbc file, which tracks the image, and this will update git ignore, and now the file is removed from the cache, and this file is again, since we don't want to track this file, add it into the. Now I'm going to add to run the prepare script. The inputs is images.tar.gc, so I put that as a dependency here. The output is this directory, data/images will contain the individual images, and we call the script to unpack. This is the command that will take this input and create these outputs. So this step added images to gitignore, so the files inside these folders are not tracked by Git, and has created a new file called dbc.yaml. As we can see here, we have name of the stage, the command that we run, the inputs, and the outputs. This file, dbc.yaml, should be tracked with Git, so we should add it to the repository. And to run the pipeline, we're going to run dbc repro, and it will detect what is missing. We only had one state, and it's going to see there's no images in the images folder, so I'm going to run the script. The script unpacks, and once it's unpacked, dbc will cache every one of the images, which are located here, are going to be stored in the dbc cache, and they are going to be linked back into my working directory. So now we are tracking this file, these individual images files, which are our training dataset. The other thing that happened is that dbc created this file, dbc log. This file saves the output of the dbc repro, so we know which is the state, the final state of running this script. We have the number of files and the total size. It also tracks the hash of the script. So if we modify the prepare script, it's going to rerun this stage. To confirm that everything is okay, we can run dbc repro again, and this time it will not do anything because nothing has changed. The input script is the same. The output files are all the same. We haven't changed them. Now, what happens if we change the output, if we delete one of these files? If we run dbc repro again, it's going to find that there are some missing files, and it's going to pull that files from the cache. So it's going to check out automatically the output from the last run, and the files will be recreated. As you can see, we have the same files I had deleted again. So these were stored initially in the cache and are now relinked into my working directory. Now let's add another stage. In this case, we're going to add a train stage that will fine-tune a convolutional neural network. This is the same code we find in the Jupyter notebook. It pulls a pre-trained network and uses fine-tuning to categorize inputs as images as cats or dogs. This script also outputs a few graphics, the confusion matrix and the top losses, and the fine-tune results. These are all plots that evaluate the error of the model. In order to add this stage, we're going to call dbc stage add. We're going to call this stage train. As inputs, we have the train script, the images in the images folder, and the outputs are two files that are the models. We can supply the plots as outputs or with the plots keyword. This will treat the outputs differently because it will let dbc know that these are things that we can compare across different iterations of our training. So if you have different trainings, you can compare the plots with different training data and parameters. Plots are usually images, and we can also use the metrics keyword to add files like CSV or txt files, and also compare those benchmarks across different runs. And finally, we call the train script to take these inputs and create this out. We can see that dvc.yaml is modified. The new stage is here with all the inputs and outputs. And to run this stage, we're going to run dvc repro. This will skip the prepare stage because nothing has changed. This process will take some time, so I will speed up the recording. So the whole process took about 15 minutes. I'm running this on my laptop, so it's not the best machine for this task, but hopefully you're using a more powerful machine. Let's check the dvc.log. We are going to see new files here due to the train stage. We're going to be the outputs, which are the plots. The models are located in the models directory. These files, because I marked them as outputs in my stage, are also ignored, so they won't be uploaded into GitHub. Same things for the files in the metrics, the images that our training generated. Now, if I want to run BBC Repro again, I'm going to skip both stages because nothing has changed. Let's try deleting some files. We can delete one of these plots, and let's also delete the model files. And if we run dvc repro again, I'm going to find these files are missing and pull them from the cache. So here they are again, and they're safe in our dvc cache. So to finish, we have the test file. The test file loads some images from Wikipedia and loads the model and tries to run the prediction. Let's add the test stage. We're going to call it test. The input is the test file, the model files, and there are no outputs. The idea is that the test file will return with an exit code different from 0 when there's an error, and it's going to exit with a 0 status code when it passes. So again, running dvc repro will only run the test, and we don't have any output, but we can check the status code, which is 0. As always, the stages are shown here in the dvc.yaml. We can also visualize the stages calling dvc. It will create a graph with all the stages and dependencies, and we can also find here in dvc.log the inputs and the outputs all hashed. So we want to also go here into a repository. We're going to add the dvc log. It's going to be tracked in git dvc yaml, or git ignores these files we have deleted, so we don't need to check them. And this one change that I made on the prepare script is superfluous, so we can undo that. So that's it. We have this. We have tracked all our process, the data that came into the training script, the outputs, the models, and the results of the test are all tracked using metadata in our Git repository. Now let's see how we can run this application. We have an application file here. We are using the Streamlit library for that, and this is a very easy way to quickly run a model in a browser. The st namespace is from Streamlit, and we are using different methods here. One for the title, to set a title. We can create a widget to upload images. This widget will show the image on screen, and we have a button to run the prediction. This will call make prediction, which loads the model and returns the probability. The model will return true or false. If it's true, it's a cat. If it's false, it's a dog. So it's going to show me that message. So to run this model, we call streamlit run on the file. Now the application is running on my machine. Let's try it by uploading one picture of my cat here. She has just woken up. And let's try the prediction. Okay, it's 99% certain that's a cat, and I think that's pretty good. So another thing we may want to do is to put this model inside a Docker container. And here we have the basic Docker file. To do this, we start from a Python container. We add an application user to not run the application as root, and copy the requirements, install them, and then copy the basically what we need here is the models, the source file, and then run the application with Streamlit. Now that the step is complete and we have committed all the files, what if we want to share this cache with my colleagues, with other team members? This is where remote storage comes in. DBC supports remote storage, and when we add a remote in the same vein as Git, we add the remote using a similar syntax, and we can upload these files, push these files into a remote repository, and other people can connect to that storage. So we have a common cache for everyone in the team, and this will, remember, have all the versions, all the iterations that everyone had done during their work, all in one place. DBC supports by default several cloud providers, and you can also bring your own. If you have a server, you can connect via SSH or using different protocols. But in my case, I will use AWS and S3 buckets. I have created an S3 bucket only for storing this example. So the syntax to add a remote is very similar to Git. DBC remote add a name. In this case, I'm going to call it origin just to keep the convention, but it can be anything. And then since I'm using S3, I'm going to prepend the bucket with S3 and the name of the bucket. Once we added the cache, we need to run DBC remote default and the name of the remote, which I called origin. And this will make that the default. And now we can push the files. If we run DBC push, we'll connect to the S3 bucket, see what's missing, and push the changes. In this case, the bucket is empty, so it will push everything we have into the remote cache. So it's starting to do that right now. So once we have everything in our repository, we can share or work with other people. They only need to add the repository, add the remote, and then run DBC. And this will pull all the changes into our local file system. Here we can see the complete workflow. We have our code and our pointers to the files in our repository, GitHub, Bitbucket, GitLab, any Git provider, and we run git pull. This pulls all the files that are the code, the pointers, the hashes, the DBC files, the dbc.yaml, everything that preserves state. Then we run dbc pull. This will connect to the remote storage and pull all the big files that are stored there, and they're going to be stored in our cache. Any changes that were made will also be synced with our local cache. Then we will run DBC repro that will run our training, fine-tuning, testing, everything we want. We can try different parameters. Then we commit all the changes. This will contain any changes with it to the code and all the new reference to the new outputs, models, plots, metrics, everything that is stored in our local cache. And this will push all these reference into Git, and then when we run dvc push, it will actually push the copy of our cache into the remote storage. Now that we have everything in a remote repository and the code in Git, we can set up continuous integration. You can use any continuous integration product. I'm going to use Semaphore because I work for Semaphore and it's the tool that I know best. So here we have our workflow editor. This lets us configure our commands. First, we're going to open the pipeline, select one of the machines that are available, and here are the commands that are going to run before each of my jobs. We're going to set the Python version, install dvc, and install the dependencies of Python and pull everything from the cache. This checkout pulls the code from Git. Then if we go to the train step, we're going to run report train. This will show only the change in the YAML file in the logs, and then we're going to push the new models into the dvc cache. And the train command will use dvc repro test. This will be the only command in this test. Remember that we put dvc pull as a common command in the pipeline. These are all the commands that are going to run before any of the jobs. So basically this job pulls the models and run the test stage. And then we have two continuous delivery pipelines. We have one for Docker that will build the Docker image and pushes to Docker Hub. Then we have a second pipeline that deploys the model into Hugging Face using Streamlit. This will pick out the code, pull the cache with all the models and run as deploy script. And we are providing environment variables. One is the address of the space, and the other is a private SSH key that we use to push the changes into the Hugging Face space. Hugging Face space uses Git and LFS to support large files. So basically this job joins everything into one repository and pushes the bundle using SSH into the Hugging Face repository. You can check the code in detail in the repository that I'm going to share in the slides, so you can download that and you will find links to blog posts, to the source code, and to the pipeline, so you can replicate that into your CI/CD system. So once I run the continuous integration pipeline and the continuous deployment pipeline, I have the application running on Hugging Face. This is, by the way, for free. You can host your models here on Hugging Face for free using different frameworks. I'm using Streamlit, which is supported by Hugging Face. And now let me again the picture just to ensure that's working. Same picture as before. Yeah, this case is even more certain that's cat. So yeah, this is one way we can deploy quickly, and this is all running in automation. We don't need to deploy manually. We just need to push our changes into the Git repository and let the CI/CD system to take over, train, and deploy for us. So that's all I have. Thank you for watching this talk. I hope it help you incorporate different tools or practices into your ML workflows. And if you want to contact me, here's my contact information, so I will be happy to talk to you. Thank you for watching and have a nice conference. Thank you.